Hello and welcome everybody, this is the MATLAB and Simulink Racing Lounge. In today's episode we are going to talk again about lap time simulation, and I'm again really glad to have a guest on board, so hi Paco.
Hi Chris,
Hi.
thank you so much for the invitation, I'm very happy to be here.
Yeah, thanks a lot. As we can see on the logo here, you're representing the TUfast team. So actually when I'm recording with teams, usually I have to do it via Skype. As the MathWorks office is in Munich, it was easy for us to join here, so good to have you here. Could you introduce your role briefly on the TUfast racing team?
Well, I've been working with TUfast for the last 2 years, and this year I'm the chief engineer for our electric vehicle.
Okay.
Exactly.
And you're basically doing lap time simulation?
And I'm in charge of the lap time simulation,
Okay.
of the further development of the
Great.
lap time simulation.
Cool. So let's move on and talk a bit about today's agenda. So what we are going to, really motivate is why is lap time simulation important? And we will see the workflow that the guys from TUfast apply. And we will see a very interesting software tool / a software demonstration. And last but not least, we talk a bit about the pros and cons of your current tool and how you possibly can improve it over time. But first, let's give Paco the opportunity to introduce briefly the TUfast racing team.
TUfast racing team was founded in 2002. We started with a combustion car, and since 2011 we also have an electric car.
Basically what I see, there's a third logo. So this is probably the TUfast Eco team. So it's a team that is participating in the
Eco Shell Marathon.
Okay.
They're building a very high efficient car.
Okay.
For the Eco Shell Marathon, and they're also very successful.
And you're sharing the same facilities and supporting each other, right?
Exactly.
Okay.
We share a bit of knowledge, and we share the facilities.
Great.
And the team, the racing team, so TUfast Combustion and TUfast SIG Technology, we're about 70 team members that are working on both cars.
Okay. Well, pretty interesting. I think now we can move into the topic right away. So why lap time simulation?
So we use lap time simulation to make better decisions when designing our car. So for example, the influence of a drag reduction system to lap time and efficiency scoring.
Whether it's worth the effort or whether you are not getting additional points from that.
Exactly.
Okay.
And also parameter sensitivity studies. So how much, for example, if I vary the mass of the car, 10% more, 10% less, how much lap time does it? How does it affect the lap time?
Okay.
And also we compare different vehicle concepts, whole concepts. For example, should I build a one-cylinder engine or a four-cylinder engine in the car?
And we will talk about that a bit later on. What is pretty new to me when I read about Aero Efficiency. So what is the relation between aerodynamics and lap time simulation?
Well, the Aero Efficiency is just the ratio between the downforce and the drag. And or we decide what efficiency we want to achieve at the end of our design to reach our maximum points, and we use the lap time simulation to get that optimum. Okay,
pretty interested to get more information on that. But before doing so, let's move on and get an overview about how you apply lap time simulation.
So we use it for different things. We, for example, isolate the parameters, like for example the vehicle mass or the engine power, and we vary them with a defined step size, and then we see how does that parameter affect the lap time. So for example, in this plot we see that with a higher weight our lap time is worse, as we would expect. And in this plot we see the engine power. So with more power we get more a lower lap time.
Okay, and what we can see, not every relation is linear. And by doing that parameter variation, you can find, let's say, the optimum. Adding a bit more weight, does it help? Is a bit more power useful? So what are the basically you're doing the sensitivity. So which parameter is most effective?
Exactly. So with these plots, we can see that a vehicle with more power is not better most of the time, because it has a certain digression where you where you get to a limit. But lowering the weight of the car, it always improves the lap time.
And basically, I can imagine that you use this information also for your, as you say, your complete vehicle concept decisions, right?
Exactly. We simulate a whole setup of a car. So, for example, a setup with a one-cylinder car and with two-cylinder engine in the car, and with the weight that each motor has, and compare the whole the complete setup to each other.
Just to understand for me, so first you do a study of the isolated parameters. You just add some weight or reduce some power, but at the end you cannot do that independently with a car. You always have impact onto other parameters. So we have put here a heavier engine, well, is perhaps more powerful, so you're affecting both. It's the power plus the weight.
So that's why we make the simulation with the whole setup of the car.
One question before moving into the software demonstration. So what is the basic what is the vehicle model in your lap time simulation?
We use a SteadyState 2-track model of the car.
Cool. Well, now I think I'm pretty interested to see how you're actually doing the lap time simulation. So let's move to the software demonstration. And I think, Paco, the stage is yours.
Thank you. So what we see here is our GUI for our setup tool, where the lap time simulation is integrated. And here, for example, we can vary the parameters of the car. So, for example, if you go to chassis and weight, we can give a weight at the front axle and the rear axle. So basically the where the center of gravity is.
It's not only your weight, you can actually specify all the masses, all the center of gravity. Okay.
Exactly, you can specify all the parameters, also the weight of the driver and the position where he's sitting. And you can also go to suspension and the geometry of the car, change the geometry of the car. And if you go, for example, to springs, you can give the stiffness of the springs and then calculate what frequency you would get with the dampers that are defined in the setup.
Okay. That's really interesting. And what I see here, the tool is quite user-friendly. You always can load data, you can update data.
Exactly. You can always go, for example, to, if we go back to chassis and then go to aerodynamics, then you can save those parameters and or load other parameters, and then everything is updated.
Great.
And you can also save and load a whole vehicle.
Okay, so what I'm seeing, the basic parameters of your car, is that your actual car, it seems to be a bit heavy to me, or are they just random parameters for our recording here?
This is a dummy that I've made. If you click here, you can import the track. For example, this is a Hockenheim 2013, and the track is calculated from data that we log from sensors, basically velocity and lateral acceleration.
Okay.
If we go to the lap time simulation, we have here a sensitivity analysis where we can, for example, vary all of the parameters like weight, and then give a minimum weight and a maximum weight, and the step size, or basically the resolution of the simulation. And
but currently we are not doing a sensitivity analysis. We have a set of parameters, and we are just running the lap time simulation for that setting.
Yes, and here on the right we have the parameters that we need for to calculate the points.
Okay, you're calculating actual points, so that's probably last year's data.
This is last year's data.
Mm-hmm. Okay, cool.
And then we can run the simulation.
Mm-hmm. So how long does a simulation run usually take?
Simulation normally takes about 20 to 30 seconds. So now the simulation is ready, and we can see here the ggV diagram. Which
so what is a ggV diagram? Just one phrase, what is it basically doing?
Basically, it tells us how much acceleration in y direction and in x direction we get for every velocity.
Okay.
So for example, if we look at the plot from this side, you see here that the maximum longitudinal acceleration is limited by the motor. So this is the motor that we gave into the simulation, and by braking, it's limited only by the tires, and we can see that here you can at higher velocities, because of the downforce, you can achieve a higher longitudinal acceleration.
It's mainly aero-related stuff here. Downforce.
Exactly.
Okay.
Everything is taken into account here. If we look at the plot from this side, you can also see the lateral acceleration for different velocities, and it's basically the same here with more downforce. Yeah. Because of the downforce at higher velocities, you can achieve higher lateral accelerations. Okay. If looked from the top of the vehicle of the diagram, you can see sort of a friction circle or a friction ellipse for the different velocities.
Okay, great. So just for me to imagine, if the parameter set is within these bounds, the car is within its current limits, so it's not yet at the limits. When it's right at the surface, the car is performing at its limits. Exactly. And when we have a parameter set out of that diagram, that's basically over the limits, something strange is happening then.
Yeah, we always simulate just at the limits. Yeah. So we don't take into account points outside.
Okay, but this is something that I can imagine is pretty important, and there are a lot of information going to that ggV diagram. It really helps you to find your car's limits, right? That's the main purpose.
The main purpose is to simulate the car always at its limit, so that we don't need the driver model.
Okay, great. So we will get back to the point later on. What else is the lap time simulation giving us? So
here we can see, for example, a plot of the lateral acceleration, and you can see that in blue is logged real data logged from the vehicle, and the red data is the simulated. And you can see that even though the parameters are not the correct ones, the car is doing pretty much the same, so the simulation is working.
Okay, so what is your decision criteria? So you say you have some log data, you're modeling a car. So when are you satisfied?
We feed some parameters that where we are not so sure if they're right, so that both of the curves have a delta of about 5% or less.
Okay, but great. This shows me that your validation is very important. And doing a parameter study on a car that is wrong, that is not representing the reality, does not make any sense. So for me, it seems like a clever first step to log and validate versus logged and real world simulated data.
Yeah, and we get different plots. This is, for example, the longitudinal acceleration. And the velocity or the speed of the car in the track, and the yaw speed.
Okay, which is basically rotation around the vertical axis.
Vertical axis of the car.
Okay.
Exactly. and also the speed plotted in through the track.
Through the track. Okay.
And here is a plot of a DRS. So in the options of the lap time simulation, we gave that we want to simulate with a DRS. And here we get the points where the DRS would be activated, would open the flaps. And this is basically, we just calculate another diagram with the DRS, and every time it makes sense to have the DRS open,
okay,
we activate it, the simulation activates it.
Okay, well, perfect. So it seems to me that you're getting a lot out of the lap time simulation. Have you been able to achieve all your goals? So you said you want to use it for concept design, you want to use it for aero efficiency. So were you satisfied, or is there still something the lap time simulation could do more or could do better?
Where for the electric car, we also use it to calculate how much energy or how big our
battery pack
has to be, and that's the development that we're making this year.
Okay.
We also want to implement torque vectoring into it.
Okay.
And
well, pretty interesting.
So that was the software demonstration.
Cool. Wow, thank you very much. What I have seen personally, this is a very professional looking user interface.
Thank you.
And it seems to me that not only specialists can use it, it's basically every team member can use it. Guys from aero, guys from suspension, they can play around with concepts and can evaluate whether it's a step forward or something they should rather not do.
Yeah, exactly. That's the plan.
How long have you been working on this lap time simulation?
For a few years.
Okay.
It's been developing. We've been developing the simulation since 2012, and then I think 2013 we made the GUI. And
okay, cool. So now what I'm really interested now, you said steady state lap time simulation, and I think now is the point where we want to get to know what the difference is to other lap time simulation approaches. So really interested to hear that.
So steady state means that we divide the track into segments, and each segment has its radius, a corner radius.
Okay.
And the point where the corner radius is minimum is defined as an apex.
Okay. So the segments are between these apexes.
Exactly.
Okay.
We have the segments are throughout the whole track.
Okay.
And at the apex, because the corner radius is minimum, we only want to have lateral acceleration, and have the highest velocity that we can only use in lateral acceleration without accelerating forward.
And this information comes from the ggV diagram.
Exactly.
Okay, cool.
So let's think about two apexes, and we have an apex 1, for example, that would be here, and an apex 2 that would be here. And from apex 1 to apex 2, we integrate the maximum longitudinal acceleration that the car can handle.
This is basically what you tell forward calculation? Okay.
Exactly. That's the forward calculation. So integrating it forward. And from the apex 2 backward to apex 1, we integrate the maximum braking acceleration.
Okay, that makes sense.
And then we overlap both of those curves that we get between those apexes, and the intersection of those curves is where the driver would have to switch between accelerating and braking. Okay,
well, so basically what you have written there is you need no driver model. This is now completely clear to me, because you're always calculating the optimum.
Exactly, we're always taking the car at its limit.
Yeah. Perfect.
So that we don't have to depend on the driver model.
Okay.
And the calculation of the car's potential is made through the ggV diagram.
Okay, you always get the information whether the car is at its maximum from the ggV. Okay.
Exactly.
So as the interface between road and car is the tire, I guess you would need a tire model.
We use a TMEC tire
Mhm.
model because it's very simple to parameterize.
Okay.
It has a very few parameters that
Okay.
you give, and it's give us our what we need.
Okay, cool. Last question on that. So are you actually doing tire testing on your own, or are you relying on data from TTC, for example?
We have gone to a test bench
Mhm.
and got data from a test bench,
Okay.
and then practically scale it or feed it
Mhm.
using test data
Okay.
of the actual vehicle.
Okay. Paco, in the agenda, we have seen also that you relate aerodynamic development and lap time simulation. So I'm pretty interested to see what your effort on your approach here is.
Yes, we also use the lap time simulation
Mhm.
to define a goal efficiency, a minimum efficiency
Mhm.
for the aero.
Mhm.
The efficiency is the ratio of downforce to drag,
Mhm.
and we want to get the optimum for scoring points.
Mhm.
And
Lift is, well, the opposite of downforce, but on the y-axis here. So you want to, well, have a higher negative lift,
exactly,
which means it's more downforce here.
exactly.
Mhm.
In this plot, for example, you can see the points in endurance,
Mhm.
and you can see that with a higher or more negative lift coefficient, you
Mhm.
get more and more points.
Mhm. Because the lines are always steeper than the ISO lines for the points.
Exactly.
Mhm.
And in the next slide, in the next plot, you can see the points for fuel efficiency,
Mhm.
and you can see that with more and more drag, you get less and less points.
Okay.
And we actually use the sum of both of those plots to get the optimum setup for endurance.
Okay, which is the just adding the points you get for efficiency plus the points you get for endurance.
Exactly.
Mhm.
And here you can see that if you develop a car close to this line, you can make sure that you're always getting more and more points. So let's say you start at this point and you develop an aero with more lift, but
Yeah.
you also get more drag.
Yeah.
You would be at this point and you would be
Yeah.
scoring less points.
Okay, so you would have a lower aero efficiency and, well, additionally you would have less points.
Exactly.
So that's pretty interesting to use it as a tool. You have a certain target aero efficiency, and every development your aero team does must be according to the target. Otherwise,
Exactly. Otherwise, it doesn't make sense, and we
okay.
would just take the arrow out.
Okay. And this is, from my point of view, a perfect engineering decision, because what we hear often, also as judges, is, well, we put an aero package on, and, well, how do you justify it? And, well, using simulation and, well, putting it in conjunction with a lap time simulation is actually very convincing. So you have technical information. Okay.
Yeah.
Well, so basically that's also new information for you guys out there. Pretty interesting. Thanks a lot. So now I think we can move into a slight discussion.
Well, the performance rating of the car shouldn't be influenced by the driver model. That's the reason why we used a steady state model. So only taking points.
Yeah.
So points in time. So that if we have different setups, it might be that a control algorithm, basically a driver model, works better with one vehicle setup than the other.
Okay.
And we want to get rid of that influence.
And you just take into account the car, no
We
matter
just-
what the driver can do.
Exactly, and
Okay.
we're always taking the car into the limit.
Yep, makes sense. Right.
It's very important also to validate the model and the simulation with log data,
Yeah.
so that we always know that the decisions we made are driven
I fully agree, because we had that point before. If you have a wrong car model, you can do a parameter study, but at the end it won't help you. So validation as a first or as an early step is pretty important.
Yeah, exactly. And we don't use the dynamic behavior. We don't take into account the dynamic behavior of the car. That's a drawback of the steady state simulation.
Okay.
So, for example, the forces and the dampers, we cannot take them into account, but we can see from the comparison between the log data and the simulation that we don't really need it.
Well, and I can imagine if you consider dynamic behavior, it would be a lot of more effort in terms of CPU time, but also in terms of development effort. You have to get so much more input data.
Yes, and we're very happy that we can simulate a setup in about 20 seconds.
Yeah, right.
And then an efficiency map.
Yeah.
For example, it takes about 20 minutes.
Yeah.
And it's done, and then we can make decisions very fast.
Okay, cool. Well, and last reason, I'm fully supporting that. Shit in, shit out. So you have to have that data. You need a tire model. You need your actual parameters of the vehicle. Otherwise, it's pretty useless, right?
Yeah, and the model also has to be good enough so that it comes out, the outcome is good.
Okay, cool. Paco, at that point, thank you very much for enlightening us further on the topic of lap time simulation. Personally, I have learned a lot new interesting things. So thanks very much.
No, thank you. Thank you again for the invitation. Yeah,
perfect. Cool. Thanks very much. And this is the point now where we move on to the last slide. You probably know that. We really are interested in your feedback. So please take the opportunity and send us an email or join our Facebook group just to get in contact with us. On the URL mathworks.com/racinglounge, you will find all episodes. I think currently we are 36 or 37. On the same page, you will also find a link to our software offer. So it's free for all former student teams. And if you do use our software, we would be really happy to see your logo on your reports and your car as well. And then, thanks for watching and see you next time. Bye.
Bye.